From space, our planet glows like a soft blue lantern hanging in the dark. Before we go any further, if you want a brand new Earth topic every single night to fall asleep to, subscribe. One tap and a new story is waiting for you every evening. Look down at that blue and white sphere from far above. You can see the clouds swirling in long white bands across the oceans. You can see the dark patches of land beneath them. And if you look closely, if you watch long enough, you can see something flickering. Tiny pulses of white light blinking in and out across the surface of the planet. They look almost like fireflies from up there. But each one of those flickers is a bolt of lightning, carrying more electrical energy than most people will use in an entire month. At any given moment, there are roughly 2,000 thunderstorms active somewhere on Earth. Right now, as you listen to this, storms are building over the warm jungles of Central Africa. They are rolling across the Gulf of Mexico. They are crackling above the mountains of Southeast Asia. The planet is never truly still. It breathes and hums and sparks, all at once, all the time. Scientists estimate that lightning strikes the Earth about 100 times every single second. That adds up to nearly 8 million strikes every day. Think about that for a moment. While you have been listening to these first few sentences, lightning has struck the Earth hundreds of times. It is one of the most common and powerful forces our planet produces. And yet, for most of human history, no one truly understood what it was. To ancient people, lightning was the voice of the gods. The Greeks believed it was a weapon thrown by Zeus from the top of Mount Olympus. The Norse people thought it was the hammer of Thor, crashing through the sky. The Aztecs, the Hindus, the Yoruba people of West Africa. Nearly every culture on Earth looked up at the same flickering sky and felt the same deep awe. That awe was not wrong. It was simply waiting for the right words to describe what was actually happening. What was actually happening is, in many ways, even more astonishing than a god throwing fire from the clouds. A thunderstorm is a living engine. It pulls warm, wet air up from the surface of the Earth and lifts it miles into the sky. As that air rises, it cools. The water inside it turns to ice. Tiny ice crystals and water droplets collide inside the cloud over and over, billions of times per second. Those collisions create an electrical charge. The cloud fills with energy the way a battery fills with power. And when that charge grows large enough, it has to go somewhere. That somewhere is the ground below, or another cloud nearby, or sometimes the open air itself. The bolt of lightning you see last only a fraction of a second. Most strikes are over in less than half a blink of an eye. But in that tiny sliver of time, the channel of air that the lightning travels through heats up to around 30,000 Kelvin. That is roughly 5 times hotter than the surface of the sun. The air around it expands so fast that it creates a shockwave. That shockwave is the thunder you hear rolling across the sky. There is something deeply calming about watching a storm from a safe place, from a porch or through a window, with the rain coming down in soft gray sheets. The sky goes dark. The air smells clean and electric. Then the flash comes, white and sharp, lighting up the whole world for just a moment. And then the low, slow rumble of thunder follows, moving through your chest like a distant drum. Storms have that effect on people. They make the world feel very large and very old. They remind us that the planet we live on is not a quiet place. It is alive with energy. It has been making lightning for billions of years, long before there were eyes to see it or ears to hear it, and in a way that scientists are still working to fully understand. That ancient lightning may have helped create the very conditions that made life on Earth possible. The storms that frightened our ancestors may have been part of the reason those ancestors existed at all. But we are getting ahead of ourselves. The storm is just beginning to build. The air is still. The sky is turning that deep, bruised shade of green and gray. Something enormous is on its way. Every thunderstorm begins with something simple. Warm air rises. That is the whole engine right there. Warm air is lighter than cool air. So when the sun heats the ground, the air just above it starts to lift. It rises the way a bubble rises through water, slowly at first, then faster. As it climbs, it carries moisture with it, invisible water vapor drifting upward into the cooler parts of the sky. This rising column of warm, wet air is called an updraft. Think of it like a slow, invisible elevator moving straight up through the atmosphere. On a calm summer afternoon, you cannot see it or feel it, but it is there and it is working. As that warm air rises higher, it cools down. And when air cools, the moisture inside it has nowhere to go. It turns back into tiny water droplets. Those droplets cluster together and form clouds. On a gentle day, this gives you the soft, white, puffy clouds that drift across a blue sky. But on a day when the air is very warm and very wet, and the atmosphere above is very cold, the updraft does not stop. It keeps pushing upward, higher and higher, building something much larger. A full thunderstorm cloud, called a cumulonimbus, can reach from just a few thousand feet above the ground, all the way up to 60,000 feet. That is nearly 12 miles straight up. To put that in perspective, most passenger planes cruise at around 35,000 feet. A mature thunderstorm cloud can tower nearly twice that high. The top of the cloud pushes up into a layer of the atmosphere called the stratosphere, where the air is so cold and so thin that the cloud spreads out flat, like an anvil being hammered wide. Pilots flying near large storms can see those flat, spreading tops from hundreds of miles away. The base of a thunderstorm cloud sits much lower, often just a few thousand feet above the ground. That dark, heavy ceiling you see rolling in before a storm is the bottom of the cloud, where the air is thick with water and the light barely gets through. The whole structure, from that low, dark base to the high, icy top, can be 10 to 12 miles tall. That is taller than Mount Everest stacked nearly twice over. Inside that cloud, the updraft is still working. Wind speeds inside a strong thunderstorm can reach 100 miles per hour or more. The air is moving violently upward through the center of the cloud, carrying water droplets and ice crystals with it. At the same time, cooler, heavier air is sinking back down along the edges. This creates a churning, cycling system that can sustain itself for hours. A single thunderstorm cell, which is one organized unit of this rising and falling air, typically lasts about 30 minutes to an hour before it weakens. But storms come alone. They often form in lines or clusters, where one cell fades and another builds beside it. A large storm system called a squall line can stretch for hundreds of miles and last an entire day, moving across the land like a slow, dark wave. The conditions that allow all of this to happen are specific. You need warm, moist air near the surface. You need cooler air above it. And you need something to give that warm air a push, to get it moving upward in the first place. That push can come from the sun heating the ground on a summer afternoon. It can come from a cold front, which is a mass of cold air pushing in and forcing the warm air up and out of the way. It can come from mountains, which force air upward simply by being in the way. Different causes, same result. Warm air rises, moisture condenses, clouds build, and the storm begins to take shape. The atmosphere is doing all of this constantly, all over the world. At any given moment, there are roughly 2,000 thunderstorms happening somewhere on Earth. That works out to about 40,000 storms every single day. The planet is never truly quiet. Even on a calm, clear night where you live, somewhere on the other side of the world, warm air is rising, clouds are building, and lightning is already flashing. It is a system that has been running for as long as Earth has had an atmosphere and liquid water. The same basic process that is building a storm over a warm ocean right now was doing the same thing 3 billion years ago. The ingredients have not changed. The physics has not changed. Only the world below the clouds has changed, slowly and enormously, in part because of the storms themselves. So the storm is building. Warm air is rising. Moisture is gathering. But what exactly is forming up there in the sky above you? What is that great dark shape that slowly swallows the blue and turns the afternoon strange and gray? The cloud at the heart of a thunderstorm has a name. It is called a cumulonimbus cloud. The word comes from Latin. Cumulus means heap or pile. Nimbus means rain cloud. A heaping, piling rain cloud. That is exactly what it looks like from the ground. It rises like a tower. It builds and builds, pushing upward with enormous force, until it reaches heights that are almost hard to picture. A fully grown cumulonimbus cloud can stretch from just a few thousand feet above the ground all the way up to 60,000 feet. That is nearly 12 miles tall. To put that in scale, commercial airplanes fly at around 35,000 feet. A mature thunderstorm cloud can rise nearly twice that high. It punches up through the layer where passenger jets cruise and keeps going, pressing into the lower edge of the stratosphere, which is the calm, cold layer of atmosphere that sits above the weather. When a cumulonimbus cloud hits the stratosphere, something interesting happens. The stratosphere is actually warmer than the air just below it, and that warmth acts like a ceiling. The rising air inside the cloud cannot punch through, so it spreads out sideways instead. The top of the cloud flattens into a wide anvil shape. Meteorologists, the scientists who study weather, actually call this the anvil top. Seen from a distance, it is one of the most striking shapes in nature. The cloud billows and churns below, and then at the very top, it fans out flat and smooth, like a blacksmith's anvil sitting in the sky. That anvil shape is a signal. It tells anyone watching from the ground that this storm has reached full strength. The cloud has grown as tall as it can grow. Now all that energy has nowhere to go but sideways, and eventually downward. Inside the cloud, the air is moving in two directions at once. Warm, wet air rushes upward through the center in powerful currents called updrafts. These updrafts can move at speeds of 100 miles per hour or more inside a severe storm. At the same time, cooler air sinks back down along the edges of the cloud in what are called downdrafts. The storm is breathing. It pulls air in from below, shoots it upward, cools it, and pushes it back down. This cycle feeds the storm and keeps it alive. The water inside the cloud is doing something remarkable during all of this. As the warm air rises and cools, water vapor turns into tiny liquid droplets. Those droplets form the visible white and gray body of the cloud. But the updrafts are so powerful that they carry some of those droplets higher and higher into regions where the temperature drops far below freezing. Up there, the droplets freeze into tiny ice crystals. The upper parts of a cumulonimbus cloud are made almost entirely of ice, not water. The cloud holds both states of water at the same time, liquid near the bottom, ice near the top, with a churning, turbulent middle where the two are constantly mixing. This mixing is not gentle. The inside of a thunderstorm cloud is one of the most violent environments on Earth's surface. Winds tear in opposite directions. Ice crystals collide with water droplets. Hailstones form and get carried back upward before they can fall. Some hailstones make this trip up and down multiple times, growing a new layer of ice on each pass, like layers of an onion. When scientists cut open large hailstones, they can count the rings and see exactly how many times that piece of ice rode the updraft before it finally fell. All of this chaos, the rising air, the freezing water, the colliding ice, the howling internal winds, is happening inside a single cloud. A cloud that from the outside might look like a slow, majestic, almost peaceful thing drifting across the sky. The stillness you see is not the whole story. The storm keeps its real work hidden inside, and that hidden work is building toward something. All that motion, all that collision, all that churning ice and water is quietly doing something to the electrical charge inside the cloud. It is sorting it, separating it, pulling positive and negative charges apart from each other, slowly and steadily, the way you might sort two colors of sand. The cloud is becoming a battery, and a battery, once charged, will eventually find a way to release what it has stored. Think about what a battery is at its heart. It is simply two sides that want to come together. A positive side and a negative side, separated by something in between. The cloud has become exactly that. Two regions of opposite charge, held apart by the air and ice between them. And the process that created this separation is one of the most quietly remarkable things that happens in our atmosphere. It begins with something almost too small to imagine. Inside the thundercloud, tiny ice crystals float near the top of the storm. Heavier chunks of soft ice, called graupel, fall slowly through the middle. When these two things collide, something passes between them, a charge. The small, light ice crystals give up electrons and carry a positive charge upward with the rising air. The heavier graupel holds onto those electrons and sinks toward the bottom of the cloud, carrying a negative charge with it. This process is called charge separation, and it happens millions of times inside a single storm, in collisions too small and too fast to see. Each tiny exchange is almost nothing on its own, but together they add up to something enormous. The top of the cloud fills with positive charge. The bottom of the cloud fills with negative charge. The cloud has sorted itself the way iron filings line up along a magnet, pulled into order by invisible forces. The negative charge at the bottom of the cloud does something else too. It pushes against the ground below. The ground is normally a mix of positive and negative charges, balanced and calm, but the heavy negative charge overhead repels the negative charges in the ground and pushes them away. What is left near the surface is a region of positive charge, sitting in the earth directly beneath the storm. The ground itself has been rearranged by the cloud above it. This is called an induced charge, and it follows the storm as it moves, like a shadow made of electricity. Now you have two things reaching toward each other: the negative charge at the base of the cloud, the positive charge on the ground below. Between them is a gap of air, roughly a mile or more of open sky. Air does not normally carry electricity. It resists it, but resistance has limits, and the charge inside a mature thunderstorm can reach hundreds of millions of volts. That is a number almost too large to hold in your mind. Hundreds of millions of volts, built one tiny collision at a time, from ice crystals no bigger than a grain of rice. The electrons that carry all this charge are ancient. They were not made here on Earth. Electrons, like all the basic pieces of matter, were forged in the first moments after the universe began. Every electron in that churning cloud has existed for nearly 14 billion years. It has been part of stars, part of dust clouds drifting between galaxies, part of the young Earth as it cooled and formed its oceans. Now it is here, inside a thundercloud over a summer field, about to take part in a flash of light bright enough to be seen from space. There is something worth sitting within that. The charge building inside this cloud is not new. It is ancient matter doing what matter has always done. moving, exchanging, seeking balance. The universe tends toward balance. Charge wants to equalize. Heat wants to spread. Water wants to flow downhill. Everything in nature is always moving toward a kind of rest. And lightning is one of the most dramatic examples of that tendency. It is the universe correcting an imbalance quickly and brilliantly. The cloud holds this charge for a while, minutes sometimes. The separation keeps building. The voltage keeps climbing. The air between the cloud and the ground is still holding on, still resisting, still acting as a wall between two things that desperately want to meet. But the wall is getting thinner. The electric field, the invisible pressure of all that charge pushing outward in every direction, is beginning to stress the air itself. It is pulling the air's own molecules apart, loosening electrons from their atoms, turning ordinary air into something that can, just barely, carry a current. The cloud is ready. The ground is ready. The air between them is beginning to give way. Everything that has happened inside this storm, the rising air, the freezing droplets, the colliding ice, the millions of tiny charge exchanges, has been leading to this single moment. The battery is full. And somewhere in the cloud, in a place too small to see, the first faint thread of the strike is about to begin its search for the ground. That first faint thread has a name. Scientists call it a stepped leader. It is not visible to the naked eye. It moves too fast and too faintly for any human to catch in real time. But it is the true beginning of every lightning bolt you have ever seen. The stepped leader is a channel of ionized air whose electrons have been knocked loose, making it able to carry electricity. It pushes down from the base of the cloud in short bursts, each one about 150 feet long. It pauses for a tiny fraction of a second. Then it steps again, down and down, branching as it goes, feeling its way through the air like roots reaching through soil. The whole process takes only about 50 milliseconds. That is 5/100ths of a second. The storm has been building for an hour. The strike takes less than the blink of an eye. As the stepped leader descends, something remarkable happens on the ground below. The strong electric field pressing down from the cloud begins to pull at everything it touches. Tall objects feel it first. Trees, buildings, hilltops, even people standing in open fields. The field is so intense that it begins to pull electrons right out of the surface of these objects, sending them streaming upward into the air. These upward streams of charge are called streamers. They rise invisibly, reaching toward the sky, searching for the descending leader above them. Most streamers never connect. They rise a few feet, maybe a few dozen feet, and then fade. But one of them, at just the right moment, in just the right place, meets the stepped leader coming down. The two channels touch, and in that instant, a complete path exists between the cloud and the ground. The circuit closes. The gate opens. What follows is called the return stroke. This is the lightning you actually see. When the stepped leader and the streamer connect, a massive surge of electrical current rushes back up the completed channel from the ground toward the cloud at roughly 1/3 the speed of light. The channel heats to about 30,000 Kelvin. That is nearly 5 times hotter than the surface of the sun. The air around it expands so fast it creates a shockwave. That shockwave is thunder. But the light comes first, because light travels faster than sound. And so you see the flash before you hear the rumble. The return stroke lasts only about 70 microseconds. A microsecond is 1/millionth of a second. In that impossibly short window, a current of around 20,000 amperes, though some strikes carry far more, tears through the air. The channel glows white, sometimes blue-white. The brightness is extraordinary. A single lightning bolt releases as much visible light as 1,100,000,000 light bulbs, all switched on at once for just that fraction of a second. And then often it happens again. The same channel, still warm and ionized, still a path of least resistance through the air, gets used a second time, and sometimes a third, and a fourth. These are called dart leaders, and they follow the same channel back down almost instantly, each one triggering another return stroke. A single lightning flash can contain anywhere from 1 to about 20 of these separate strokes. They happen so quickly that your eye blends them together into one flickering bolt. But a high-speed camera would show each stroke as its own distinct pulse of light. This is why lightning appears to flicker. It is not one event. It is several, stacked on top of each other in a fraction of a second, each one reusing the same glowing path through the air. The whole system, from the first invisible step of the leader to the final return stroke, is a machine built by physics. Pressure and charge and heat and the basic rules of electricity all work together. The cloud does not choose where to strike. The ground does not choose to receive it. The stepped leader does not plan its path. Every branch, every pause, every connection between leader and streamer happens because of invisible forces following invisible rules. And yet, the result is one of the most dramatic sights in the natural world. A bolt of lightning is the sky solving a problem. The charge was separated. The voltage climbed too high for the air to hold back, and so the air gave way, and the electricity found its path. And for one brilliant instant, the gap between cloud and ground simply ceased to exist. The imbalance, built over minutes of furious storm activity, corrected itself in less time than it takes to draw a breath. That brilliant instant is shorter than most people imagine. A full lightning bolt from the very first invisible leader reaching down from the cloud to the final return stroke blazing back upward lasts only about a second, sometimes less. The part you actually see, the bright channel of light, lasts just a fraction of that. We blink our eyes in roughly a third of a second. Lightning is faster than that. It is over before your eyelid has finished closing. And yet, in that fraction of a second, something extraordinary happens to the air. The channel of lightning, the glowing tube through which all that electricity travels, is surprisingly narrow. Most lightning bolts are only about as wide as your thumb. Some are thinner than a pencil. When you see a photograph of a jagged white bolt splitting the sky, the bolt itself is not as wide as it looks. What you are seeing is mostly glow, the light bleeding outward from the channel into the surrounding air. The actual path of electricity is slender and precise. Now think about how tall that pencil-thin channel is. A typical lightning bolt stretches between 1 and 5 miles from cloud to ground. Some bolts are longer. Scientists have recorded lightning channels that travel more than 60 miles horizontally across the sky. If you laid one of those long bolts on the ground, it would stretch from one end of a major city to the other. And all of that distance, all of those miles, are crossed in less than a second. The temperature inside that narrow channel is where the numbers become almost impossible to hold in your mind. Lightning heats the air around it to roughly 50,000 degrees Fahrenheit. That is about 5 times hotter than the surface of the sun. The surface of the sun glows at around 10,000 degrees. Lightning, in that thin thread of space, no wider than your thumb, burns 5 times hotter than that. The sun, of course, sustains that heat across an enormous sphere, nearly 1,000,000 miles wide. Lightning holds that temperature only for a moment, in a channel you could almost cover with your hand. But for that moment, it is one of the hottest things on Earth. That heat does something remarkable to the air. It expands the air outward at incredible speed. The air around the channel does not warm slowly. It explodes. In a fraction of a second, the air is forced outward in every direction from the bolt. That sudden, violent expansion is exactly what creates thunder, which we will visit very soon. But even before the sound reaches you, the light does. And the light arrives almost instantly, because light travels at 186,000 miles per second. There is essentially no delay between the bolt and the flash you see. The brightness of that flash is hard to compare to anything familiar. A single lightning bolt releases enough light energy to power a 100-watt light bulb for about 3 months. All of that energy released in a fraction of a second through a channel the width of your thumb. The flash is so intense that it can cast sharp shadows even in the middle of the day. At night, a nearby strike can briefly turn darkness into something brighter than noon. There is one more detail about the shape of lightning that rewards a slow look. The branching pattern, those forking arms that split and split again as they reach toward the ground, follows a pattern found all through nature. River deltas branch the same way. The roots of trees branch the same way. The blood vessels in your lungs branch the same way. Scientists call this kind of pattern fractal, meaning the same branching shape repeats at smaller, and smaller scales. The whole bolt looks like a branch. Each branch looks like a smaller bolt. Each smaller bolt branches again. The electricity moving through air and finding the path of least resistance draws the same shape that water draws moving through soil, that roots draw pushing through rock. Different forces, different materials, the same elegant solution. A bolt of lightning is, in one sense, a tiny thing, thinner than a pencil, gone in less than a second. And in another sense, it is enormous, miles long, hotter than the sun's surface, bright enough to blind, loud enough to shake the ground beneath your feet. It is easy to think of lightning as simply a flash of light in a dark sky, but up close, in the details, it is something far stranger and more precise. A narrow thread of almost unimaginable heat, tracing a fractal path through the air, solving in an instant what the storm spent minutes building. And then the light is gone. The bolt vanishes in less than a second. The sky goes dark again. But the storm is not finished with you yet. Something else is coming. Something slower, deeper, and in its own way just as astonishing as the flash itself. Thunder. Most people think of thunder as simply the sound that follows lightning. A loud noise, a warning, something to count while you wait for the next flash. But thunder is much more than that. It is the voice of the air itself, torn open and then snapping shut. Here is what happens. When lightning strikes, it heats the air around it to roughly 30,000 degrees Fahrenheit. That is about 5 times hotter than the surface of the sun. The air does not warm slowly. It heats in a fraction of a second. And air that heats that fast does something dramatic. It expands. Explosively, it blasts outward in every direction at once, faster than the speed of sound. That sudden, violent expansion is the crack of thunder. The air around the bolt is not just warm, it is shocked. Scientists actually call this a shock wave, meaning a wave of pressure so powerful it moves faster than sound itself. That sharp crack you hear when lightning is very close, that hard, splitting sound like a giant piece of wood breaking. That is the shock wave arriving almost directly. The bolt was near. The air had almost no time to slow down before it reached you. But when the storm is farther away, something softer happens. The shock wave travels through miles of air. It bounces off clouds, off hills, off the ground. It spreads out. By the time it reaches your ears, that sharp crack has softened into something longer and lower. A rumble, a rolling, deep groan that seems to come from everywhere at once and fade slowly into silence. The same explosion, the same torn air, but stretched and scattered by distance into something almost gentle. Thunder does not come from one single point. A lightning bolt can be a mile long, sometimes 2 miles, sometimes more. Every inch of that bolt heats the air at the same moment. So the sound comes from the entire length of the bolt all at once. The part of the bolt closest to you sends its sound first. The parts farther away send their sound a little later. All of that sound arrives at your ears in a long, staggered wave. That is why thunder rumbles and rolls instead of arriving as one clean sound. You are hearing the whole length of the bolt, one piece at a time. The low, rolling quality of distant thunder comes partly from something else too. Low-pitched sounds, the deep bass notes, travel farther through air than high-pitched ones. The sharp crack of a close strike contains many different pitches all at once. But as that sound travels, the higher pitches fade first. By the time the thunder has traveled several miles, mostly the low tones remain. The distant storm speaks in a lower voice than the close one. Sound travels through air at roughly 1,100 feet per second. That is about 1 mile every 5 seconds. Lightning travels at nearly the speed of light, which means it arrives at your eyes almost instantly, no matter how far away it is. So the gap between the flash and the thunder tells you exactly how far away the bolt was. 5 seconds of silence means 1 mile. 10 seconds means 2 miles. The storm is writing its distance in the pause between light and sound. There is something almost musical about this. The sky is sending you 2 signals at once, one in light and one in sound, and the space between them is a kind of message. The universe is measuring itself for you, using nothing but the rules of physics and the patience to count. Thunder can sometimes be heard from as far as 10 miles away under the right conditions. A quiet night, flat land, cool air close to the ground. The sound carries farther when the air is still. On a busy afternoon in a city, that same thunder might only reach you from 5 miles out before the noise of the world swallows it. And sometimes, on very still nights, you can hear something even stranger. A low, almost continuous murmur from a distant storm you cannot see. The lightning is beyond the horizon. The light never reaches you at all, but the thunder, rolling and low, travels just far enough to arrive as a faint, soft sound at the edge of hearing. The storm is invisible, but it is speaking. And if you are quiet enough, you can hear it. That low murmur from a storm beyond the horizon is one of the quieter wonders of a stormy night. But there is a way to bring the storm closer, at least in your mind. A way to reach out across the dark and measure exactly how far away it sits. You already know the first part. Light travels almost instantly. Sound takes about 5 seconds to cover 1 mile. So you count the seconds between the flash and the rumble, divide by 5, and the storm tells you its distance. Simple, elegant. A piece of physics you can do in your head while lying still. But the deeper you look at this, the stranger and more interesting it gets. Sound does not travel at the same speed in all conditions. Temperature changes everything. In warm air, sound moves a little faster. In cold air, it slows down. The 5-second rule is a very good estimate, but it is built on an average. On a hot summer evening, the sound of thunder might reach you just slightly sooner than you expect. On a cold autumn night, it arrives just a little late. The difference is small, a fraction of a second per mile. But it is real, and scientists who study acoustics, the science of how sound behaves, account for it carefully. Humidity plays a role too. Moist air carries sound differently than dry air. A storm rolling in off a warm, wet coastline will sound slightly different from a storm crossing a dry inland plain. The air itself shapes the message before it reaches you. There is something else happening beneath the surface of all this. Thunder does not come from one single point. A lightning bolt can stretch for miles across the sky. Every inch of that bolt is superheating the air around it at the same moment. So the sound does not come from one place. It comes from the entire length of the strike, all at once, from near and far. The closest part of the bolt reaches your ears first. The farthest part arrives a few seconds later. This is why thunder rumbles and rolls instead of arriving as one sharp crack. You are hearing the full length of the lightning bolt stretched out in time, near end first and far end last. A very close strike, one directly overhead, can sound like a single explosive crack. There is almost no distance between you and the bolt. The whole sound arrives nearly at once. But a strike that crosses the sky at an angle, stretching away from you as it goes, produces that long, slow, rolling growl. The rumble is the shape of the lightning, translated into sound. Deep inside a thunderstorm, the sound is doing something else entirely. It is bouncing. The underside of the cloud acts like a ceiling. The ground acts like a floor. Thunder echoes between them, reflecting back and forth, losing energy with each bounce. By the time it reaches you, it has already traveled a complicated path. It has bounced off hills, skimmed along valleys, reflected from the surface of a lake. What you hear is not just the original sound. It is a layered collection of arrivals, each one a slightly different version of the same moment. Scientists who study infrasound, which is sound pitched so low that human ears cannot hear it at all, have found that thunderstorms produce these ultra-low vibrations too. They travel enormous distances, hundreds of miles. Instruments sensitive enough to detect them can pick up a storm long before any visible sign of it appears. The storm announces itself in frequencies the human body cannot consciously register. Some researchers believe animals can sense these vibrations, that cattle lie down before a storm, not because of some mysterious instinct, but because they feel the infrasound arriving in their bodies before the sky shows any sign of change. The storm is always speaking in more languages than we can hear, and all of this, the rolling rumble, the echoes, the infrasound traveling silently across hundreds of miles, all of it begins with a single flash. A channel of superheated air no wider than your thumb. The lightning bolt itself lasts less than a second, but the sound it makes spreads outward in every direction, bouncing and bending and fading, carrying information about the storm's size and distance and shape to anyone patient enough to listen. The sky is not just something to look at. It is something to read. And thunder is one of the oldest texts on earth, written fresh every time a storm rolls through, waiting for anyone who knows how to count. When lightning strikes the ground, most people think the story ends there. The bolt arrives, the thunder follows, the storm moves on, but the ground beneath your feet has its own part to play, and it begins the moment that channel of electricity makes contact with the earth. The soil and rock below the surface are not perfect conductors. They resist the flow of electricity. So when a lightning bolt drives its charge into the ground, that energy does not simply disappear. It spreads outward from the strike point in rings. The way a stone dropped in still water sends ripples in every direction. This spreading current is called ground current, and it moves through the earth in a wide, shallow dome, radiating out from where the bolt landed. That ground current can travel surprisingly far. Within a radius of roughly 100 feet from a strike, the voltage difference between 2 points on the ground can be large enough to be dangerous. This is why standing near a tree that has just been struck carries real risk. Even if the bolt never touched you directly, the earth itself carries the charge outward, and anything in its path becomes part of the circuit. Animals with 4 legs face a particular danger from ground current that humans do not. A 4-legged animal standing on the ground has its front feet and back feet separated by a greater distance than a person's 2 feet. That greater distance means a greater voltage difference between the front and back legs. Livestock in open fields have been killed by lightning strikes that landed many feet away, not because the bolt hit them, but because the ground current passed through their bodies from one set of legs to the other. It is one of the quieter, less visible ways that a storm leaves its mark on the land. The charge does not only spread outward along the surface. Some of it drives downward, following the most conductive paths it can find. Underground water, wet clay, mineral veins, the roots of trees, all of these can guide the current deeper into the earth. A single strike can send electricity threading through root systems and along buried rock formations, traveling through pathways that no human eye will ever see. This is where the cycles of lightning connect to something much older and much slower. Over thousands of years, repeated lightning strikes in the same region gradually alter the chemistry of the soil. Lightning produces nitrogen oxides as it superheats the air, and rain washes those compounds into the ground. Soil that has been struck repeatedly over long periods carries a slightly different chemical signature than soil that has rarely seen a storm. Scientists studying ancient landscapes can sometimes find traces of this history written into the earth itself, evidence of storm patterns that played out long before any human was watching. The ground also stores a record of lightning in a more dramatic form. When a bolt carries enough energy and strikes sandy or silica-rich soil, it can fuse the material around the strike channel into a glassy, hollow tube. These tubes are called fulgurites, from the Latin word for lightning. They form in seconds, preserving the exact shape of the channel, the electricity carved through the earth. Some fulgurites are only a few inches long. Others extend several feet down into the ground, branching and narrowing as they go. A frozen record of a moment that lasted a fraction of a second. Finding a fulgurite is like finding a fossil of electricity. The bolt is long gone. The thunder has faded, but the shape of the strike remains, locked in glass, waiting in the quiet dark beneath the surface. This is the rhythm that the directive of this section points toward. Lightning is not just a single event. It is part of a cycle that moves through the air, through the surface, through the soil, through the chemistry of the ground, and back up again into the atmosphere. The charge that builds in a cloud, releases in a bolt, spreads through the earth, and slowly dissipates, is part of a global electrical circuit that scientists believe has been running continuously for as long as Earth has had an atmosphere. The planet itself carries a slight negative charge on its surface, balanced against a positive charge in the upper atmosphere. Lightning is one of the mechanisms that keeps that balance from drifting too far in either direction. Every storm that rolls across a continent, every bolt that that drives into the ground, every ring of current spreading silently through wet soil. All of it is part of the planet's own quiet housekeeping. The earth breathes electricity the way it breathes carbon and water, in long, slow cycles that connect the sky above to the ground below and back again. The sea has its own relationship with lightning. It is quieter than you might expect, and stranger. When a bolt strikes the ocean surface, the energy does not vanish. It spreads. Water conducts electricity far better than dry land does, and so the charge from a single strike fans out in every direction at once, moving across the surface in a wide, invisible ring. On land, a bolt drives deep into the soil and the current narrows. In the sea, the current stays near the surface and travels outward, thinning as it goes, covering a much wider area before it finally fades. This matters enormously to the creatures living there. A fish or a sea turtle swimming near the surface, when lightning strikes, can feel that spreading current from many meters away. Marine animals are sensitive to electrical fields in ways that land animals simply are not. Sharks, for instance, have special organs along their snouts called ampullae of Lorenzini, tiny jelly-filled pores that can detect the faintest electrical signals in the water. These organs help sharks hunt, but they also mean that a shark near a lightning strike feels the pulse of it in a way that is immediate and physical. Scientists believe most marine animals instinctively dive deeper when a storm approaches, sensing the change in pressure and electrical charge in the water long before the first bolt ever falls. The ocean's surface itself changes during a thunderstorm. The rain that hammers down during a heavy storm is slightly acidic, carrying dissolved gases from the atmosphere. When this rain hits the sea, it delivers small amounts of nitrogen compounds directly into the upper layer of the water. Lightning also produces nitrogen oxides as it tears through the air, and some of those compounds dissolve into the sea when they fall with the rain. Nitrogen is a nutrient. It feeds the tiny floating organisms called phytoplankton, which drift near the surface and form the base of nearly every ocean food chain on Earth. A single large storm can deliver a quiet invisible pulse of nourishment to the sea below it. The ocean and the atmosphere are always exchanging things: gases, heat, moisture, and yes, chemistry born from lightning. The sea breathes in what the sky produces. Coastal regions feel this exchange most directly. Storms that build over warm ocean water carry enormous electrical energy. Tropical thunderstorms, the kind that form over the warm Atlantic or the western Pacific, are among the most electrically active storms on Earth. The warm, wet air over the tropics rises fast and hard, feeding towering clouds that can reach 12 or 15 kilometers into the sky. These clouds generate lightning at a furious rate, and because they often sit directly over the sea for hours or even days before making landfall, much of that lightning strikes water rather than ground. Scientists who study global lightning patterns have found that the ocean actually receives fewer lightning strikes per square kilometer than land does. This surprised many researchers when the data first came in. The reason seems to be that land heats up faster than water during the day, creating stronger updrafts. The rising columns of warm air that power thunderstorms. The sea stays cooler and more stable. But when ocean storms do form, they tend to be large and long-lived, and the lightning they produce can be intense. There is something almost meditative about imagining a storm far out at sea, with no land in sight. The clouds build in the afternoon heat, dark and enormous, their tops flattening against the upper atmosphere. The wind picks up. The surface of the water goes from deep blue to gray-green, and then the lightning begins, bolt after bolt striking the open water, each one sending its silent ring of current spreading outward in the dark below the surface. No one watches. No one hears the thunder except the storm itself. The fish have gone deep. The birds have gone to shore. The sea accepts the electricity the way it accepts everything quietly and without complaint. The ocean covers more than 70% of Earth's surface. It is the planet's largest neighbor to every storm that has ever formed. And it does not simply receive what the sky sends down. It shapes the storms themselves. The heat rising off warm tropical water is the fuel that builds the clouds. The moisture moisture that evaporates from the sea is the water vapor that freezes into ice crystals high in the cloud. The same ice crystals that collide and separate and build the charge that eventually becomes lightning. The sea makes the storm. The storm strikes the sea, and the energy moves on into the water, into the creatures, into the chemistry, into the slow turning of the world. Lightning is not always white. Most people picture it that way, that bright, sharp flash cutting across a dark sky. And yes, most lightning does appear white or pale blue to the human eye. But lightning wears many colors, and each one tells a story about what the bolt is passing through on its way to the ground. When lightning travels through dry air, it tends to burn a clean, bright white. The air has little moisture to scatter the light, so the bolt appears almost pure. But when that same bolt pushes through air heavy with rain, the light scatters differently. Water droplets in the air bend and spread the wavelengths of light, and the lightning takes on a softer, more yellow tone. Some bolts appear orange. Some appear a deep, warm red. These are not tricks of the eye. They are the physics of light moving through different kinds of air. The color blue appears when lightning travels through clear, cold air at high altitude. Up near the top of a storm cloud, where the air is thin and the temperatures drop far below freezing, the electrical discharge burns with a cooler, sharper blue. Scientists have photographed these high-altitude bolts in detail, and the blue is unmistakable. A clean, electric color that looks almost artificial against the black of the upper sky. Green lightning is rarer still. It appears most often at the edges of severe thunderstorms, particularly near hail. Hail forms when water droplets are carried high into a cloud by strong updrafts and freeze into pellets of ice. Those pellets contain tiny amounts of certain minerals and particles. And when a bolt passes near a region of heavy hail, the light can take on a faint green cast. Witnesses who have seen green lightning often describe it as eerie, something that feels wrong, like a color that does not belong in a storm. But it belongs. It is simply rare. Perhaps the most dramatic color lightning can wear is purple. Purple lightning tends to appear when a bolt travels through air with high humidity, and and a mix of nitrogen and oxygen, excited by the electrical charge. Nitrogen, the gas that makes up most of Earth's atmosphere, glows violet when electricity passes through it. This is the same principle behind neon signs, where electricity excites gas inside a tube, and the gas responds with light. The sky itself is a kind of tube. The lightning is the electricity, and sometimes the sky glows purple. There is also lightning that glows red, and this kind is different from the red tint that rain-scattered light can produce. High above the tops of thunderstorms, far above where any airplane flies, there are electrical phenomena called sprites. Sprites are large, faint, reddish flashes that shoot upward from the tops of storm clouds toward the edge of space. They last only a fraction of a second. They are enormous. Some sprites stretch for tens of miles, but they are so brief and so high that humans on the ground almost never see them. Pilots first reported seeing strange red flashes above storms decades ago, but scientists did not capture clear images of sprites until 1989, when a camera accidentally recorded one during a research flight. The scientific community had to see the photograph before they fully believed the pilots. Sprites are not the only strange lights above the storm. There are also blue jets, which shoot upward from the tops of clouds in narrow cones of blue light. And there are elves, a name that stands for emissions of light and very low frequency perturbations due to electromagnetic pulse sources, which is a long way of saying rings of faint light that spread outward at the edge of the atmosphere like ripples on water, triggered by the electromagnetic pulse of a lightning strike far below. These rings can be hundreds of miles wide. They last less than a millisecond. Most of them go unseen. The storm, it turns out, does not only send its energy downward, it sends it upward too. The lightning that strikes the ground is the part we know. But above the cloud, the storm is painting the upper atmosphere in colors that almost no one ever sees. Red sprites, blue jets, rings of light expanding silently at the boundary between sky and space. All of this from a storm. All of this from ice crystals colliding inside a cloud, from charge building slowly in the cold, dark air, from the same basic process that makes your socks stick together in the dryer. The scale changes, the colors change, but the electricity is the same quiet force, finding its way through whatever it is given, wearing whatever color the air allows. And yet, for all the lightning we can measure and map and predict, there are still things that happen in a storm that science has not fully explained. The strangest of these is something called ball lightning. Ball lightning is exactly what it sounds like. A glowing ball of light floating in the air, moving slowly, sometimes passing through walls or windows, sometimes vanishing with a soft pop, sometimes exploding with a sharp bang. People have reported seeing it for centuries. It appears in colors ranging from pale white to deep red to vivid blue. It can be the size of a golf ball or the size of a beach ball. It drifts. It hovers. It behaves nothing like the lightning we know. Scientists have collected thousands of eyewitness reports. The descriptions are remarkably consistent across different countries and different centuries. People describe a glowing sphere that moves against the wind, that passes through solid objects, that lasts anywhere from a few seconds to nearly a minute before fading or bursting. A normal lightning bolt lasts less than a second. Ball lightning, if it is real, lingers. It stays. It seems almost curious. The reason scientists still debate it is simple. No one has ever captured clear, controlled footage of ball lightning in a laboratory setting. It appears without warning. It vanishes just as fast. A few photographs exist, and a small number of video clips, but none of them are definitive. In 2014, a team of researchers in China recorded what they believe was ball lightning using spectrometers, which are instruments that measure the chemical makeup of light. The data suggested the glowing ball contained silicon, iron, and calcium, which are all elements found in soil. This led some scientists to suggest that ball lightning might form when a regular lightning bolt vaporizes minerals in the ground, sending a cloud of glowing plasma, which is superheated gas, briefly into the air. But this is still a theory. The mystery is not solved. What makes ball lightning so quietly wonderful is not just the strangeness of it. It is the reminder that even something as well studied as lightning still holds corners we have not fully lit. The storm is not finished surprising us. There are other small exceptions worth pausing on. Lightning does not always travel in a single straight bolt. Sometimes it branches into dozens of thin channels at once, spreading outward like the roots of a tree seen from above. This branching happens because the stepped leader, which is the invisible channel of ionized air that forms just before a strike, does not always find the shortest path on its first try. It sends out multiple branches simultaneously, feeling its way through the air. Only one branch completes the circuit. The others simply stop, frozen in the sky for a fraction of a second before fading. What we see as a single bolt is often the winning branch of a race we never knew was happening. Sometimes lightning strikes the same place many times within a single storm. The Empire State Building in New York City is struck by lightning roughly 20 to 25 times per year. During a single storm, it can be struck multiple times within minutes. This happens because tall structures create a reliable path for the return stroke. The air around them is already ionized from previous strikes. The path of least resistance is already open. Lightning, given the choice, will use a road it already knows. There is also a phenomenon called a positive lightning strike, which is rarer and far more powerful than the negative lightning that accounts for most strikes. Positive lightning originates from the top of the thundercloud rather than the bottom. It travels much farther through the air to reach the ground, sometimes striking miles away from the storm itself, in areas where the sky appears almost clear. Because it travels so far, it carries a much larger electrical charge. A positive lightning bolt can carry 10 times the energy of a typical negative strike. It is responsible for a disproportionate number of wildfires and fatalities. It arrives without the usual warning signs. The sky looks calm. Then the ground shakes. These are the quiet details, the branching leaders that lose their race, the glowing sphere that drifts through a kitchen and vanishes, the bolt that falls from a clear sky miles from the nearest cloud. They are not the main story of a thunderstorm. They are the footnotes, but sometimes the footnotes are where the most interesting things live, tucked quietly at the edge of what we understand, waiting for someone patient enough to look closely and ask why. The storm holds more than it shows. It always has. For a long time, no one knew how many times lightning struck the earth. People had watched storms for thousands of years. They had named the lightning, feared it, worshipped it. But counting, it was another matter entirely. The sky is vast. Storms move fast. And lightning does not wait to be measured. The first serious attempt to understand lightning as a physical force came in the 18th century. Benjamin Franklin is the name most people remember. In the 1750s, he proposed that lightning was electricity, the same force that made a glass rod spark when you rubbed it with cloth. This was a remarkable idea. Most people at the time believed lightning was divine. Franklin believed it was natural. He was right. His famous kite experiment, conducted around 1752, helped demonstrate that storm clouds carried electrical charge. It was dangerous work. A Swedish scientist named Georg Wilhelm Richmann tried a similar experiment in 1753 and was killed by the electrical discharge. Franklin survived. His work opened a door that has never closed. But knowing that lightning was electricity was only the beginning. Actually counting how often it struck the earth was a far harder problem. You cannot stand in a field and tally every bolt. Storms happen everywhere at once, over oceans, over mountains, over forests where no one is watching. For most of human history, the true number was simply unknown. The real breakthrough came in the 20th century. Scientists began building networks of sensors, devices placed across wide areas that could detect the electromagnetic pulse, the burst of energy that every lightning bolt releases the moment it forms. These pulses travel through the air at the speed of light. By measuring when the pulse arrives at several different sensors, scientists could calculate exactly where and when the strike occurred. This method is called lightning detection, and the networks built to do it now cover most of the planet. What those networks revealed was astonishing in its scale. Lightning strikes the earth roughly 100 times every single second. That adds up to about 8 million strikes per day. And somewhere close to 3 billion strikes per year. The number is so large, it is almost hard to hold in your mind. While you take a slow breath in, lightning has struck the ground more than 100 times somewhere on this planet. The clearest view of this came from space. In the 1990s, NASA launched satellites carrying instruments designed specifically to detect lightning from orbit. The optical transient detector, and later, the lightning imaging sensor, gave scientists something they had never had before: a full, continuous picture of lightning activity across the entire globe. From hundreds of miles above the Earth, these instruments could see every flash, day and night, over land and sea. The maps they produced were beautiful and strange. Lightning was not spread evenly across the world. It clustered in specific places, following patterns tied to heat, moisture, and the shape of the land. Central Africa, particularly the region around the Congo Basin, showed the highest lightning density on Earth. The warm, wet air rising over the forests there creates ideal conditions for thunderstorms almost every afternoon. Venezuela's Lake Maracaibo is another extraordinary hotspot. Storms there produce lightning so frequently and so reliably that sailors once used the glow on the horizon as a navigation aid. The phenomenon even has a name: Catatumbo lightning, named for the river that flows into the lake. On some nights, the sky above the lake flashes hundreds of times per hour for hours on end. The satellites also confirmed something that ground-based sensors had suggested. About 75 to 80% of all lightning never touches the ground at all. It stays inside the cloud, flickering between regions of opposite charge in the dark interior of the storm. Only the remaining fraction makes the full journey down to Earth. The strikes we see and hear, the ones that split trees and shake windows, are a small portion of the total electrical activity happening above our heads. What strikes you when you sit with these numbers is how alive the atmosphere truly is. It is not empty space between the ground and the stars. It is a churning, electrical, endlessly active system. Every second, somewhere on this planet, a bolt of lightning is completing a circuit between the sky and the ground, releasing energy, shaking the air, briefly connecting two parts of the world that are usually very far apart. Franklin stood in a field with a kite and a key and asked a simple question. What is this thing? 2.5 centuries later, we have satellites watching every flash from orbit, and the sky is still answering. When lightning finally reaches the ground, something remarkable happens in the soil beneath your feet. The bolt does not simply pass through and disappear. It leaves a mark. It changes the very material it touches, sometimes in ways that last for thousands of years. The temperature of a lightning bolt at the moment of contact is roughly 30,000 Kelvin. That is about 5 times hotter than the surface of the sun. This heat arrives in less than a millisecond. The soil, the rock, the sand, whatever the bolt meets, has almost no time to respond. And so, instead of simply heating up and cooling down, the material transforms. It melts. It fuses. It becomes something new. When lightning strikes sandy soil, the intense heat can melt the grains of silica, the tiny particles of quartz and mineral that make up most sand, and fuse them together into a glassy tube. This tube is called a fulgurite, from the Latin word for thunderbolt. A fulgurite forms in the shape of the lightning's path through the ground, branching and twisting downward like a frozen root. Some fulgurites are only a few centimeters long. Others have been found stretching more than 4 meters into the earth, following the exact route the electricity chose in a fraction of a second. They are fragile, pale, and hollow inside. They look like something a glass blower might make, except no human hand shaped them. The storm did. What surprises most people is that the lightning does not stop at the surface. The current spreads outward through the ground in all directions from the point of contact, moving in a pattern that scientists call a ground current. This spreading electricity is genuinely dangerous. An animal or person standing near a strike point, even if they are not directly hit, can be injured or killed by the current moving through the earth beneath them. Livestock in open fields are especially vulnerable for this reason. The current enters through one leg and exits through another, completing a circuit through the body. This is why, during a storm, the safest position if you are caught outdoors is to crouch low with your feet together. reducing the distance between contact points and limiting the path the current can travel. The ground current also does something quieter and stranger. It can travel along buried pipes, tree roots, and even the water table, the layer of groundwater that sits beneath the soil. Scientists have measured electrical pulses moving through groundwater systems after nearby strikes. The Earth, it turns out, is a conductor. It carries the charge onward, spreading the energy of a single bolt across a much wider area than the visible flash would suggest. Lightning also leaves chemical changes behind. When a bolt passes through air, it breaks apart nitrogen molecules, the pairs of nitrogen atoms that make up most of our atmosphere. These broken atoms recombine with oxygen to form nitrogen oxides. When those compounds fall to earth with rain, they dissolve into the soil as nitrates. Nitrates are a form of nitrogen that plants can actually absorb and use. This means lightning is, in a very real sense, fertilizing the ground. Every storm that rolls across a field deposits a small amount of usable nitrogen into the soil below. Before humans invented synthetic fertilizers, lightning was one of the primary ways that nitrogen entered ecosystems in a form that living things could use. The storm was feeding the forest long before anyone understood why. There is one more thing lightning does to the ground that took scientists a long time to accept. When a powerful bolt strikes certain types of rock, particularly rocks that contain iron minerals, it can briefly magnetize them. The intense magnetic field generated by the current passing through the rock aligns the iron particles inside, leaving a faint but measurable magnetic signature. Geologists have found these signatures in ancient rocks and used them to identify lightning strike sites from thousands of years ago. The ground holds the memory of the storm, written in the language of magnetism. Long after the thunder has faded and the sky has cleared, so the bolt that flashes for a millisecond is not finished when the light goes out. It has melted glass into the sand. It has spread current through the soil. It has broken apart molecules and fed the roots of trees. It has written its name in stone. Lightning does not simply visit the ground. It changes it, quietly and permanently. stories we are still learning to read. The earth beneath a storm is not a passive surface waiting to be struck. It is a partner in the exchange, absorbing the sky's energy and carrying it forward in forms that last long after the clouds have gone. Trees feel the storm long before it arrives. The air around them changes. The pressure shifts. And when lightning finally reaches down and finds a trunk, the transformation is immediate and total. When a bolt strikes a tree, the energy has nowhere to go but through. Wood is not a great conductor of electricity, so the current does not flow smoothly. Instead, it races along the thin layer of water and sap just beneath the bark. That narrow channel of moisture carries the full force of the strike in a fraction of a second. The water inside the tree turns instantly to steam. The pressure of that steam is enormous. It blows the bark outward in long strips, sometimes hurling pieces dozens of feet away. What remains is a tree with a deep spiral groove carved from crown to root, like a giant hand twisted it from above. That spiral pattern is not random. Trees grow in a gentle twist as they reach upward toward the sun. Their grain follows a slow spiral, year by year, ring by ring. When lightning travels through that spiraling grain, it follows the path the tree itself laid down over decades. The storm and the tree are, in a strange way, working together. The bolt reads the shape of the wood and carves along its natural lines. The tree's whole life is written in that groove. Some trees survive. Oaks and other trees with thick, deeply furrowed bark sometimes endure a strike and keep growing. The wound heals over slowly, the bark closing around the scar like a hand closing around a stone. Other trees are not so fortunate. The force of the steam explosion can split a trunk completely, leaving two halves standing apart like open doors. But even a fallen tree struck by lightning becomes something new. It becomes shelter, habitat, and food for beetles, fungi, and mosses that would never have reached it otherwise. The storm opens the tree, and the forest moves in. Sand tells a different story. When lightning strikes dry, loose sand, particularly the kind found on beaches or in open deserts, the heat is so extreme that it fuses the grains together. bolt carves a narrow tube of melted glass down through the sand, following the path of the current as it seeks the ground. These tubes are called fulgurites, from the Latin word for thunderbolt. They are fragile, hollow, and rough on the outside, but glassy and smooth within. They branch and fork underground, following the same branching patterns as the lightning bolt above. A fulgurite is, in a sense, a fossil of the strike itself. It is the shape of the lightning, preserved in glass, buried in the earth. Fulgurites can be surprisingly long. Some extend several feet below the surface. Others have been found stretching much deeper. The longest ever recorded reached nearly 17 feet into the ground. That is the distance from the surface all the way down, captured in a single frozen moment of heat and pressure. Researchers study fulgurites to understand how lightning behaves underground, how the current spreads and branches, and how much energy the ground absorbs. Each one is a record of a storm that may have passed centuries ago. Stone, too, carries the mark. In rocky mountain environments, lightning strikes exposed peaks and ridgelines again and again over thousands of years. The repeated heating and cooling of rock causes it to crack and fracture over long stretches of time. Lightning helps break down stone into smaller pieces. Those pieces eventually become part of the soil. Minerals locked inside the rock are released. They wash downhill with rain, carried into streams and rivers, and eventually spread across the land. The lightning that strikes a mountain peak in one century may help feed a meadow in the next. This is the quiet work of the storm. It is not only a flash of light and a crack of sound. It is a sculptor working in wood and glass and stone. It reshapes the surfaces it touches and sends the results moving through the world. A tree's scar becomes a beetle's home. A beach's sand becomes a glass tube that scientists study in a laboratory. A mountain's rock becomes the soil of a valley. The energy that fell from the sky does not disappear. It passes into the material world and keeps moving, changing form again and again. Lightning connects the sky to the ground, yes, but it also connects the ground to everything that grows in it, everything that lives on it, and everything that will come after. The storm reaches down, and the the world reaches back, and something new is made from the meeting. That exchange has been happening for billions of years. It is still happening right now, somewhere beneath a darkening sky. And that exchange goes back much further than most people realize. Long before the first tree stood on land, long before the first fish swam in the sea, lightning was already at work. It was doing something even more remarkable than carving wood or melting sand. It was helping to build the very ingredients of life itself. The early earth was a strange and violent place. About 4 billion years ago, the atmosphere was nothing like the air we breathe today. It was thick with gases like methane, ammonia, water vapor, and hydrogen. There was very little oxygen. The sky was not blue. It was a murky, heavy shroud of chemicals, and storms raged across it constantly. Lightning struck the surface again and again, day after day, for millions of years. Scientists believe that those ancient bolts did something extraordinary. When lightning passed through that early atmosphere, it carried enormous energy. That energy broke apart the molecules in the air, those tiny building blocks of matter, and forced them to recombine in new ways. The result, scientists think, was the formation of amino acids. Amino acids are the small chemical units that link together to form proteins. And proteins are the foundation of all living things. In 1953, 2 scientists named Stanley Miller and Harold Urey tested this idea in a laboratory. They filled a glass chamber with the gases believed to exist in the early atmosphere. Then they sent electric sparks through the mixture to mimic lightning. Within days, amino acids had formed on their own. The experiment did not create life, but it showed that lightning could create the raw materials that life is built from. That result still stands as one of the most striking findings in the history of science. The Earth was essentially a chemistry lab, and lightning was the spark that kept the reactions going. Over millions of years, those amino acids may have collected in warm, shallow pools or along ocean shorelines. They may have linked together into longer and longer chains. Slowly, over vast stretches of time, those chains grew more complex. Scientists still debate exactly how life began. But many believe that lightning played a role in setting that process in motion. This is one of the quieter wonders of the storm. The same force that splits a tree on a summer evening may be a distant cousin of the force that helped write the first chapter of life on this planet. The lightning bolt you see tonight is part of a story that began before anything alive existed to witness it. And lightning has not stopped shaping life since then. Even today, every bolt that strikes the ground does something that living things depend on. It fixes nitrogen. Nitrogen is a gas that makes up most of our atmosphere, but plants cannot use it in its raw form. Lightning breaks apart nitrogen molecules in the air and forces the nitrogen to combine with oxygen. This creates compounds that fall to the ground with rain. Once in the soil, those compounds become a form of nitrogen that plants can actually absorb and use to grow. This process is called nitrogen fixation, and it is one of the ways the planet feeds itself. Lightning contributes a meaningful portion of the fixed nitrogen that enters ecosystems around the world each year. Every time a storm passes over a forest or a field, it is quietly delivering a kind of natural fertilizer. The plants do not know where it came from, but they use it all the same. The atmosphere itself has changed because of life, and life has changed because of the atmosphere. And lightning has been woven through both sides of that slow exchange for billions of years. The oxygen we breathe today came largely from ancient photosynthetic life, tiny organisms that transformed the early atmosphere over hundreds of millions of years. But the chemistry that helped spark those first living things may have begun in a storm. There is something deeply settling about this. The same energy that rumbles across the sky on a rainy night has been part of Earth's story since nearly the beginning. It is not separate from life. It is connected to life at a level so deep and so old that it is almost impossible to fully picture. Lightning did not build life on its own. The ocean helped. The sun helped. Chemistry helped. Time helped more than anything. But the storm was there. It was present at the very start, crackling through a young and restless sky, breaking things apart and letting them come back together in new forms. That is what lightning has always done. It disrupts, it transforms, and in that transformation, something new becomes possible. Long before the first rumble reaches human ears, the animals already know. There is something remarkable about the way living creatures read the air. They do not need instruments or weather reports. They carry their own quiet sensors, built by millions of years of living close to storms. And the signals they detect are written in light, in pressure, in electricity, in the very same forces that build the storm itself. Birds are among the first to notice. Many species can detect infrasound, sound waves so low and so slow that human ears cannot register them at all. Thunderstorms produce infrasound from enormous distances, sometimes hundreds of miles away. A flock of birds may grow restless and take to the sky hours before a storm arrives, responding to a sound that no person in that field can hear. They are reading a message written in frequencies too deep for us. But birds also read the light. The sky before a storm changes color in ways that are subtle but real. As a storm system builds, the atmosphere scatters light differently. The air thickens with moisture and rising particles. Sunlight filters through at a lower angle and a longer wavelength. The world takes on that particular greenish or golden cast that many people recognize from memory, that strange, heavy glow that feels like a held breath. Birds see a wider range of color than humans do. They can detect ultraviolet light, which is invisible to us. The sky before a storm likely looks very different through their eyes, richer, stranger, more urgent. Insects respond to the electrical charge in the air. As a storm builds, the electric field near the ground shifts. The air becomes more charged. Bees, which are extraordinarily sensitive to electric fields and use them to navigate between flowers, begin to behave differently. They return to the hive earlier than usual. Their movements become shorter, more deliberate. Scientists believe bees can sense the rising electrical tension in the atmosphere well before the storm arrives. The hive goes quiet. The foragers come home. Sharks and rays carry a sense that most animals do not have at all. They can detect extremely weak electric fields through special organs called ampullae of Lorenzini, tiny jelly-filled pores clustered around their snouts. These organs evolved to help them find prey hiding in sand. But they also make sharks sensitive to changes in the ocean's electrical environment. When lightning strikes the sea, as it does thousands of times each day, it sends pulses of electrical energy through the water. Some researchers believe sharks may respond to these pulses by diving deeper, moving away from the surface where the electrical disturbance is strongest. The ocean's top predators retreating from the sky. Even earthworms feel the storm coming. When barometric pressure, the weight of the air pressing down, begins to drop before a storm, the soil shifts. Moisture levels change. Earthworms, which breathe through their skin and must stay moist to survive, begin moving toward the surface. A lawn covered in earthworms after a storm is a familiar sight, but some of them were already moving before the first drop fell, responding to changes in the soil that the storm sent ahead of itself like a quiet announcement. The light of a coming storm is not just a visual signal. It is part of a whole system of warnings that the natural world has learned to read over enormous stretches of time. The greenish sky, the heavy golden glow, the strange stillness that settles over a forest before the first crack of thunder. These are not coincidences. They are the storm announcing itself through every channel it has. And the animals, shaped by long experience with exactly this kind of sky, have learned to listen. Cats and dogs often grow anxious before a storm arrives. Some researchers think this is partly due to static electricity building in their fur. A dog's coat can accumulate a small charge as the atmosphere's electric field intensifies. Some dogs seek out grounded surfaces, bathtubs, tile floors, as if they are trying to discharge that uncomfortable feeling. They are not imagining the storm. They are feeling it, literally, on their skin. There is something deeply moving about this. Every creature on Earth lives inside the same electrical atmosphere. The same forces that build a thundercloud, that separate charge and send a bolt crashing to the ground, also hum quietly through the bodies of birds and bees and sharks and worms. The storm does not arrive as a surprise to the living world. It arrives as a familiar presence. Something old, something known. The animals lift their heads and they turn toward the darkening sky, and they begin to move. There is a place on earth where the storm never ends. Near the mouth of the Catatumbo River in Venezuela, where the river meets a wide lake called Lake Maracaibo, lightning strikes almost every single night. It has been doing this for as long as anyone can remember. Local people have watched it for centuries. Sailors once used its glow to navigate in the dark. They called it the Lighthouse of Maracaibo. No flame, no oil, no keeper climbing stairs. Just the sky cracking open again and again, casting pale light across the water. Scientists have measured this storm carefully. Lightning strikes here on roughly 260 nights per year. On a single active night, the sky above Lake Maracaibo can produce up to 40,000 individual lightning bolts. That number is almost impossible to hold in your mind. 40,000 strikes in one night, in one place, while most of the world sleeps. The reason this happens comes down to geography. Warm, wet air flows in from the Caribbean Sea and moves across the flat land toward the Andes Mountains. The mountains stop that air from going any further. It piles up, rises, cools, and builds into enormous thunderclouds night after night. The lake itself adds moisture to the air. The surrounding swamps add more. Everything about this place is perfectly shaped to make storms. The land and the water and the mountains have been working together for thousands of years to produce this endless electric light show above the water. The sound above Lake Maracaibo on those nights is something few people ever hear. Thunder rolls continuously, one crack folding into the next before the first one fades. It is not the sharp, sudden boom of a nearby strike. It is a low, constant rumble, like the earth itself is clearing its throat. Distant thunder has a softer quality than close thunder. The high-pitched crack of a nearby bolt gets absorbed by the air as sound travels. What remains after a long distance is mostly the deep, rolling bass. The sound arrives in waves, one after another, without pause. This kind of persistent storm has a name. Scientists call it a a mesoscale convective system, which simply means a large, organized weather system that keeps generating new thunderstorm cells as older ones weaken. The Catatumbo storm is one of the most reliable examples on the planet. It is not one storm that never ends. It is a cycle of storms, each one born from the same geography, the same warm air, the same mountains standing in the way. New cells rise, old cells fade. The lightning continues. There is another kind of endless storm, though this one is quieter, around the entire planet. At any given moment, roughly 2,000 thunderstorms are active at once. Together, they produce about 100 lightning strikes every single second. This means that while you are reading one calm sentence, lightning has struck the earth more than 100 times somewhere. The planet is never truly still. There is always a storm somewhere, always a bolt reaching down, always a rumble moving across some distant plain or ocean. These constant storms do something important. Each lightning bolt produces a small amount of nitrogen oxide, a gas that eventually helps fertilize soil. Across millions of years, the continuous drumbeat of global lightning has quietly fed the ground. The storms are not just dramatic events. They are part of how the earth maintains itself, how nutrients cycle through the air and into the land, how the chemistry of the atmosphere stays in balance. The sound of all this, if you could hear it all at once, would be extraordinary. But there is a way to listen to something close. Scientists study a phenomenon called Schumann resonances, which are extremely low-frequency electromagnetic waves that bounce between the Earth's surface and the upper atmosphere. Lightning generates these waves. They circle the globe continuously, like a very slow heartbeat. Sensitive instruments can detect them anywhere on Earth. When researchers convert these signals into audio, the result is a deep, slow hum. The planet itself is vibrating gently, driven by the constant activity of thousands of storms. It is one of the quieter facts about our world. The earth hums, not loudly, not in a way you would ever notice standing outside on a calm evening, but the signal is there, steady and real, generated by every storm on the planet working together. The Catatumbo lightning, the afternoon storms over the Congo, the squall lines moving across the open Pacific, all of them feeding the same low frequency, all of them contributing to the same planetary pulse. The storm that never stops is not just one place in Venezuela. It is everywhere. It is always. That planetary pulse does not belong to Earth alone. When you look up at the night sky and see the other worlds hanging there, pale and distant, it is easy to think of them as quiet places, still, cold, unchanging. But many of them crackle with electricity, just as our own atmosphere does. Lightning is not a feature unique to Earth. It is something the universe does again and again, wherever the right conditions gather, and the numbers behind it are extraordinary. Saturn is perhaps the most dramatic example. Scientists, using the Cassini spacecraft, which orbited Saturn for 13 years, detected lightning storms on that planet that were thousands of times more powerful than anything we experience here. A single Saturnian lightning bolt can carry energy roughly 10,000 times greater than a typical bolt on Earth. The storms that produce them can stretch across thousands of kilometers of cloud. One storm system, observed in 2010 and 2011, wrapped almost entirely around the planet. It lasted for months. The radio signals it produced were so strong that instruments on Cassini could detect them clearly from far away. Saturn does not whisper when it storms. It roars. Jupiter is no quieter. The Voyager spacecraft first detected lightning on Jupiter back in 1979, picking up radio bursts that matched the signature of electrical discharge deep in those swirling clouds. Later, the Juno spacecraft flew close enough to gather detailed measurements. Scientists found that Jovian lightning, the lightning of Jupiter, tends to cluster near the poles rather than the equator. This is the opposite of what happens on Earth, where most lightning occurs in the tropics. The reason comes down to heat. On Earth, the sun warms the equator and drives the storms. On Jupiter, the planet generates its own internal heat, and that heat rises most effectively near the poles, creating the towering storm clouds that lightning needs. The same basic rule, heat driving air upward, plays out on a completely different world in a completely different way. Uranus and Neptune also show signs of lightning, though they are so far away that our measurements are harder to confirm. The evidence suggests that deep in Neptune's atmosphere, where pressures are enormous, water and ammonia may combine in ways that allow electrical charge to build and release. Scientists believe that on these ice giants, lightning may occur far below the visible cloud tops, hidden inside layers of atmosphere we have never directly seen. Even Venus, our nearest neighbor, may host lightning. This has been debated for decades. Early Soviet probes that descended through the Venusian atmosphere detected signals that some researchers interpreted as lightning. More recent missions have added to the evidence. Venus has thick clouds made of sulfuric acid, and those clouds may generate charge just as water ice clouds do on Earth. The confirmation is still not complete, but the possibility is real. A world with no liquid water on its surface, blistering hot, wrapped in poisonous clouds, may still find a way to spark. What makes all of this so elegant is the underlying simplicity. Lightning requires only a few things. It needs a fluid medium, a gas or liquid that can move. It needs particles that can collide and separate charge. It needs enough vertical motion to keep those particles apart long enough for the charge to build. That is the entire recipe. And the universe, it turns out, provides those ingredients in many places. The same basic physics that sends a bolt from a summer cloud in Ohio to a cornfield below also sends electricity arcing through the ammonia clouds of Jupiter. The numbers scale up or down. The molecules involved may differ, but the underlying rule stays the same. There is something deeply calming about that. The universe runs on a small set of elegant principles, and those principles repeat. They show up on every world with an atmosphere. They show up in the lab when you shuffle your feet across carpet and touch a doorknob. The scale changes by billions. The rule does not. Researchers estimate that lightning strikes Earth about 40 to 50 times every second across the solar system. That number grows considerably. Saturn alone may produce lightning at rates that dwarf our own planet's activity. When you add Jupiter, Neptune, Uranus, and possibly Venus. The total number of lightning events happening right now across just our small corner of the galaxy becomes almost impossible to picture. And beyond our solar system, there are billions of other planets. Many of them likely have atmospheres. Many of those atmospheres likely churn with storms. The same quiet spark that lights up a summer sky over a sleeping town is probably happening right now, in some form, around stars we will never visit, on worlds we have not yet named. For most of human history, lightning was simply a mystery. It came from the sky. It killed without warning. It set forests on fire and split ancient trees in half. People built stories around it. They gave it to gods. They prayed before storms and sheltered in fear. The idea that a person could understand lightning, let alone control where it struck, would have seemed impossible for most of recorded time. Then came Benjamin Franklin. In the 1750s, Franklin had a simple but remarkable idea. He believed lightning was not a supernatural force. He believed it was electricity, and he believed that if electricity naturally sought the tallest point in an area, then a tall metal rod connected to the ground by a wire could give lightning a safe path to follow. The charge would travel down the rod, through the wire, and quietly into the earth. No fire, no destruction, just a quiet transfer of energy. He was right. Franklin's lightning rod was one of the most practical inventions in human history. Buildings, barns, and ships that once burned regularly in storms could now be protected with a simple metal spike and a length of copper wire. The invention spread quickly across Europe and America. Tall structures that had been vulnerable for centuries were suddenly safe. Churches, which had long been struck because of their height, were among the first buildings to benefit. What makes this invention so elegant is how well it fits the way lightning actually behaves. Lightning is always looking for the path of least resistance, meaning the easiest route for electricity to travel. Metal conducts electricity far more easily than wood, stone, or air. So when a lightning rod sits at the top of a building, the electrical charge in the air naturally flows toward it. The rod accepts the strike. The wire carries the current safely down. The ground absorbs it. The building stands untouched. Modern lightning protection systems work on the same basic principle Franklin described. They are more refined now. Engineers calculate the exact placement of rods, the thickness of the grounding wire, and the depth of the earth connection. Tall buildings in cities like New York and Chicago are struck by lightning dozens of times each year. The Empire State Building alone is struck roughly 20 to 25 times annually. Because of its protection system, almost none of those strikes cause any damage at all. The building simply accepts the energy and lets it pass. Airplanes are struck by lightning more often than most people realize. Commercial aircraft are hit by lightning roughly once every 1,000 flight hours on average. That sounds alarming, but modern aircraft are designed to handle it. The metal skin of a plane conducts electricity around the outside of the fuselage, the main body of the aircraft, and away from the passengers and electronics inside. Engineers call this a Faraday cage effect, named after the scientist Michael Faraday, who showed that a hollow conductor, meaning a shell of conducting material, shields whatever is inside from electrical charge. The lightning enters the plane's surface, travels along the outside, and exits without ever reaching the interior. The same principle protects people inside cars during storms. The metal shell of a vehicle conducts the charge around the outside. The passengers inside are shielded. It is not the rubber tires that protect you, as many people believe. It is the metal body of the car acting as that same kind of conducting shell. What is remarkable about all of this is how much protection we have built around a force we still cannot fully predict. Scientists can tell you where storms are likely to form. They can track a storm's movement with great precision. They can measure the electrical charge building inside a cloud. But they cannot tell you exactly which tree, which rooftop, or which open field will receive the next bolt. Lightning makes its final decision in a fraction of a second, along a path that forms in real time. The randomness is real, and yet the system holds. The rods stand ready. The wires run down to the earth. The ground accepts what the sky sends down. Franklin's idea was not just clever. It was a recognition that nature follows rules, and that if you understand the rules, you can work with them instead of against them. There is something quietly wonderful about that. A storm builds for hours. Billions of volts of electrical charge accumulate inside a cloud the size of a mountain. And at the end of all that power, a thin copper wire, no thicker than a finger, is enough to guide it safely home. The force is immense. The solution is simple. And the balance between them is, in its own way, very beautiful. And yet, for all we have learned, lightning still holds its secrets close. Scientists have studied storms for centuries. They have built instruments to measure electric fields, launched weather balloons into the hearts of thunderclouds, and tracked lightning bolts with cameras that shoot thousands of frames per second. They have learned an enormous amount. But the more closely they look, the more questions appear. This is not a failure of science. It is what science actually looks like up close. Every answer opens a door to something new. One of the biggest open questions is deceptively simple. We still do not fully understand exactly how a thundercloud builds its charge in the first place. The leading theory involves ice crystals and soft hail colliding inside the cloud, trading electrical charge the way two pieces of fabric trade static when you rub them together. But the details of how that process scales up to billions of volts remain unclear. Scientists can describe the general shape of the answer. The precise mechanics, though, are still being worked out. This is why storm chasers exist. Not just for the drama of it, though there is certainly that. Storm chasers are often scientists, or they work alongside scientists, driving instrumented vehicles into the path of severe storms to collect data that no satellite or weather station can gather from a safe distance. They carry sensors that measure electric field strength, wind speed, pressure, and temperature all at once. They position themselves close enough to a storm to capture details that matter. And then they try very hard not to get struck by the thing they are studying. The work is genuinely dangerous. Tornadoes and lightning are not the only hazards. Large hail can shatter windshields in seconds. Flash floods can appear without warning on a road that looked dry moments before. And the the storms themselves can change direction faster than a vehicle can respond. Several storm researchers have been killed in the field. The scientific community remembers them. Their data, gathered at great personal risk, helped build the models we use today. One project that changed the field was called STEPS, the Severe Thunderstorm Electrification and Precipitation Study. It ran in the early 2000s across the high plains of the United States, where flat terrain and warm, moist air from the Gulf of Mexico create some of the most powerful thunderstorms on Earth. Researchers flew aircraft directly into storm cells, measuring charge distributions inside clouds with extraordinary precision. What they found surprised them. The electrical structure inside a storm is far more complex than the simple positive on top, negative on bottom model that most textbooks describe. There are multiple charge layers, shifting and reorganizing as the storm evolves. The cloud is not a simple battery. It is something much stranger. That complexity helps explain why lightning prediction remains so difficult. Even with all our tools, we cannot reliably forecast a specific strike more than a few seconds before it happens. Researchers are working on systems that can detect the electrical buildup inside a cloud and issue very short-range warnings, measured in minutes rather than hours. Some of these systems are already in use at airports and outdoor event venues, but they are still far from perfect. There are also phenomena that scientists have only recently confirmed exist at all. Sprites are large, faint flashes of red and orange light that appear above thunderstorms, reaching up into the upper atmosphere, sometimes as high as 50 miles above the ground. They last only a few milliseconds. For decades, pilots reported seeing them, but no one could capture clear evidence. It was not until the 1990s that a camera accidentally recorded one, and the scientific world had to accept that something entirely new had been sitting above every major storm, invisible to anyone, not looking in exactly the right direction at exactly the right moment. Elves are another such phenomenon, named with a quiet sense of humor by the researchers who first described them. An elf is a dim, expanding ring of light that spreads outward from the top of a lightning discharge at the speed of light, reaching a diameter of nearly 300 miles in less than a millisecond. They are caused by the electromagnetic pulse from a lightning bolt interacting with the lowest edge of the ionosphere, the electrically charged layer of the upper atmosphere. They were confirmed in the 1990s as well. Scientists now believe they occur with a significant portion of all lightning strikes. We simply never noticed them before. The sky above a storm turns out to be just as active as the storm itself, and most of that activity was invisible to us until very recently. There is something genuinely humbling about that. We have been watching thunderstorms for all of human history, and we are still learning to see them. Storms have always shaped the world, not just the ground beneath them, but the course of human events. History is full of moments where a single storm arrived at exactly the right time and changed everything that followed. In 1281, a massive Mongol fleet set sail to invade Japan. The fleet carried over 100,000 soldiers. It was one of the largest naval forces ever assembled in the ancient world. Then, a typhoon struck. The storm destroyed most of the fleet and ended the invasion entirely. The Japanese called that storm the kamikaze, which means divine wind. Japan remained unconquered. The entire future of that region shifted because of weather. Storms have ended sieges, scattered armies, and delayed voyages that might have changed the map of the world. The weather was not a background detail in those moments. It was the deciding force. And lightning, specifically, has left its mark on human history in ways both large and small. It has started wildfires that reshaped forests and drove migrations. It has struck trees that fell across rivers and changed the course of floods. It has ignited grasslands that burned for weeks, clearing land that humans and animals then moved into. Long before people understood what lightning was, it was quietly editing the world around them. Now look forward, not just decades, but deep into the future. What happens to lightning when the world itself begins to change? Earth's climate is warming. The atmosphere is holding more heat and more moisture than it did a century ago. Scientists have studied how this affects storm activity, and the findings are striking. Research suggests that for every degree Celsius the planet warms, lightning activity may increase by roughly 10%. That is not a small number. It means more strikes, more fires started by lightning, more nitrogen deposited into the soil by each bolt. The whole system scales up. In a warmer world, thunderstorms may grow taller and more powerful. The updrafts inside a storm, those fast-rising columns of warm air that drive the whole engine of a thundercloud, will have more energy to work with. Taller clouds mean more distance for ice and water to collide and separate charge. More charge means more lightning. The storms of the future may be more electric than anything humans have seen in recorded history. Over thousands of years, the continents themselves will continue to drift. They move slowly, only a few centimeters each year, but over millions of years, that adds up to enormous change. The arrangement of land and sea controls where storms form and where they travel. As continents shift, the ocean currents that carry warm water around the globe will shift too. New storm corridors will open, old ones will close. The patterns of lightning that have held steady for millions of years will gradually rearrange themselves across the face of the planet. In roughly 250 million years, scientists believe the continents may merge again into a single large landmass. This has happened before in Earth's history. When all the land is bunched together, the interior of that supercontinent becomes a vast, dry region far from any ocean. Storms need moisture. They need warm, wet air rising from the sea. A world with one giant continent would have enormous dry zones where thunderstorms almost never reach. The lightning map of that future Earth would look nothing like the one we know today. And further still, in about 5 billion years, the sun will begin to expand. It will grow into what astronomers call a red giant, swelling outward until it engulfs the inner planets. Long before that happens, Earth's oceans will begin to evaporate. Without liquid water, the water cycle stops. Without the water cycle, there are no thunderstorms. The lightning that has crackled through Earth's atmosphere for 4 billion years will finally go quiet. But even then, the story does not end. The atoms that made up every storm, every bolt of lightning, every raindrop will still exist. They will scatter into space. Some of them may eventually become part of a new planet forming around a younger star. And on that planet, if conditions are right, water may gather, clouds may form, and lightning may strike again. The same process that may have helped spark the first living molecules on this earth could begin again somewhere else, in some distant corner of the galaxy, billions of years from now. Lightning is not just a feature of this planet. It is a feature of the universe. Wherever the right ingredients gather, wherever charged particles move through gas and moisture, the spark finds a way. It always has. It always will. The storm is patient. The storm is very, very old, and it has a long way still to go. Step outside on a clear night, far from city lights. Look up. The sky above you is not empty. It is full of information, written in a language that humans have been learning to read for thousands of years. Long before scientists had instruments, people read the sky to survive. Sailors watched cloud shapes to predict safe passage. Farmers studied the color of the horizon at dawn. Indigenous cultures across every continent developed deep, careful knowledge of weather patterns passed down through generations. This was not superstition. It was science built from careful observation over centuries. The sky really does tell you what is coming. A ring around the moon, caused by ice crystals high in the atmosphere, often signals that a warm front is approaching. Warm fronts carry moisture. Moisture feeds storms. That simple ring of pale light is the first quiet warning that something is building far above. Clouds are the sky's most honest messengers. The tall, dark towers of a cumulonimbus cloud, the kind that carries lightning, can reach 10 miles into the air. From the ground, they look like enormous dark mountains. Their tops flatten out into the shape of an anvil when they hit the upper atmosphere, a layer called the tropopause, where rising air can go no higher. When you see that flat anvil shape spreading across the sky, a thunderstorm is already fully formed. The lightning is already happening inside. The color of the sky before a storm carries meaning too. A greenish tint in the sky especially in the late afternoon, sometimes appears before severe storms. Scientists believe this happens because the deep blue light of a clear sky mixes with the reddish-orange light of the setting sun, filtered through the yellow-green water vapor inside a towering storm cloud. It is one of the stranger and more beautiful warnings the atmosphere can offer. Wind shifts are another signal. Before a thunderstorm arrives, the wind often changes direction suddenly. This happens because the storm pulls air inward as it grows, the way a drain pulls water. That sudden shift, that change in the feel of the breeze on your skin, is the storm breathing in. Ancient sailors knew this feeling. They called it the breath of the storm. They were not wrong. Pressure drops before a storm arrives. The air actually gets lighter. Some animals feel this change before any human instrument can measure it. Sharks dive deeper. Birds stop singing. Cattle gather together. Bees return to their hives. The whole living world responds to a shift in pressure that most humans walk right past without noticing. The atmosphere is always broadcasting. The question is whether anything is listening. Lightning itself, once you know how to read it, tells you a great deal. The shape of a bolt can reveal the structure of the air it traveled through. A forked bolt that branches many times means the air had many different pockets of charge. A single clean stroke means the path was more direct. Scientists can study the geometry of a lightning bolt the way a doctor reads an X-ray, finding information about the invisible structure of the storm, hidden inside the shape of the light. The time between the flash and the thunder tells you distance, but the direction of the thunder, the way it rolls and echoes, can tell you the shape of the storm. A sharp crack means the lightning was close and the bolt was nearly vertical. A long, low rumble means the bolt was long and horizontal, and the sound reached you from many points along its length at slightly different times. The storm is speaking in geometry. All of this, the clouds, the colors, the wind, the pressure, the animals, the shape of the bolt, and the sound of the thunder, is one connected system. Each piece of information links to every other piece. The atmosphere is not a collection of separate events. It is one enormous, living, breathing machine. every part of it is in conversation with every other part. Reading the sky is really just learning to hear that conversation. It is noticing that the ring around the moon and the shift in the wind and the silence of the birds are all saying the same thing. Something is coming. The air is changing. The charge is building. Humans have always looked up. We have always tried to understand what the sky was telling us. And the sky has always been generous with its answers. If we are patient enough to look and quiet enough to listen, the storm does not arrive without warning. It announces itself slowly, beautifully, in 100 different ways. All you have to do is learn the language. And once you do, you will never look at the sky the same way again. And then, quietly, the storm passes. The thunder fades to a low murmur somewhere far to the east. The rain slows to a soft tapping on leaves and rooftops. The sky, which was dark and heavy just an hour ago, begins to open. A pale strip of light appears along the horizon. The air smells clean and sharp, the way it always does after a storm. That smell has a name. It is called petrichor, and it comes from oils in the soil mixing with rainwater and rising into the air. It is one of the oldest smells on Earth. Humans have been breathing it in after rainstorms for as long as there have been humans. There is something in us that recognizes it. Something that relaxes when it arrives. The storm has done its work. It has moved millions of gallons of water from the ocean into the sky and back down to the land. It has cooled the air. It has fed the rivers. It has charged the soil with nitrogen, a key building block that plants need to grow. Every bolt of lightning that struck the ground during the storm helped fix nitrogen from the air into the earth. Scientists estimate that lightning adds around 100 million tons of nitrogen to the soil every single year. Without it, the land would be far less fertile. The storms are not just dramatic events. They are part of the reason the fields are green. The clouds begin to thin and separate. Stars appear between them, one at a time, like small lights being switched on in a very large room. The moon, if it is out, casts long silver lines across puddles on the ground. Everything is still. Everything is resting. Somewhere in the distance, another storm is forming. Right now, at this very moment, there are roughly 2,000 thunderstorms happening across the Earth. The planet is never fully quiet. There is always somewhere that the sky is building charge, always a cloud climbing upward, always a bolt reaching down. The atmosphere is always at work. But here, in this particular patch of sky, the work is done for now. The air has balanced itself. The charge has been released. The pressure has eased. The earth continues to spin. It always does. One full rotation every 24 hours, steady and unhurried, carrying every ocean and mountain and sleeping city along with it. From space, the planet looks like a small blue marble wrapped in white cloud. Storms swirl across its surface like slow, graceful spirals. They look peaceful from that distance. Everything does. The galaxy that holds our small planet is called the Milky Way, and it contains somewhere between 100 and 400 billion stars. Our sun is just one of them. A quiet, medium-sized star sitting near the edge of one of the galaxy's arms, carrying its little family of planets through space at roughly 515,000 miles per hour. We do not feel that speed. We feel only the stillness of a night after rain. The universe is about 13.8 billion years old. The Earth is about 4.5 billion years old. The first thunderstorms on this planet happened billions of years ago, long before there were eyes to see them or ears to hear them. They crackled over a young, hot world, helping to build the chemistry that would eventually lead to life. Every living thing on Earth carries, somewhere deep in its history, a debt to those ancient storms. And now here we are, breathing the clean air, watching the clouds drift apart, listening to the last of the rain drip from the edges of rooftops and branches and leaves. The world is very old. The storms are very old, and we are very small and very new and very lucky to be here at all, looking up at a sky that has been putting on this show for billions of years without ever stopping. There is something deeply comforting in that. The storms will come and go. The sky will darken and lighten. The lightning will flash, and the thunder will roll, and the rain will fall, and the air will clear. It has always been this way, It will be this way long after any of us are here to watch it. For now, the storm has passed. The sky is quiet. The earth is resting. And somewhere above the thinning clouds, the stars are out, steady and calm, the way they have always been. You can rest now too. Subscribe for a brand new Earth topic every night, one tap, and something wonderful is waiting for you tomorrow. Sweet dreams.